Yes. Okay. Hello, Spencer. Hello, Connor. And just put focus on the screen. Hello, Jared, and then you'll be here in a minute. So, and hello to everyone who is watching. Hello to everyone who is watching it in the recordings. So, the lecture is kind of boring. We need to go through it, but main thing that we need to accomplish today is to feel the. We need to feel the sign up list. So we are in the middle of fourth chapter, and it was in previous year. By this time, we already did third presentations, so it's about time to do it. So I plan to make it come Monday, right? And today we will fall in this country's time to practice democracy. So you practice choices which subject you want to present. And then I will mumble something related to oscillators, and then we'll continue this stuff regularly as we do. So here is the list. As please log in and try to put in your choices. So if you Spencer was quick. Okay. Yeah, thank you for making choices. And let's continue filling it so I can quickly go over it so that we feel more comfortable. And all these materials were either discussed with Zane and Jared. One, two, and who's with us today? Else? Connor. So Connor, please consider to place your name somewhere in here. And whoever is not on the meeting, I will just place randomly. And even if you made selection, I can make suggestion because there are some complicated subjects, and I trust on your help in covering them. So briefly, so that you do not feel discomfortable, Connor, please consider to type your name somewhere. And from time to time, we are solving time-dependent linear equation to predict future to see how the wave packet, either of electronic or nuclear nature, propagates forward in time. This is superior compared to time-independent linear equation. At the very beginning, we did cover so-called evolution operator technique. The code implements evolution operator technique. The input parameters are potentials that tells which molecular system we describe, and initial conditions of the wave packet, what its shape, localization, momentum, and then it shows how the wave packet propagates in a given potential. This is not optional. The main component of the grade will be based on the independent research projects, which will be based on using this code for different models. So right now you are accumulating the main part of the course. Before we go to interesting and important research thing, we need to master our skill in understanding how the code is working and what are the background principles. So these materials are chopped based on the principles how the code is working. It is not computational class. We are not We do not need to be professional programmers, but we need to get general idea what are the equations and principles behind the code and how to manipulate it by changing some minor parameters. Okay, yeah, thank you, Connor. Yeah. Okay, at least we have four choices, and there is no guarantee that you will be literally doing what you selected, but chance is high. Many thanks. Let me maybe copy right away. Copy slides. Very good. And I will post process. So we have more than half, like half of the schedule is already is ready. Okay, let's go forward. So there is a little pathetic homework. Of course, I do not discourage anyone to do it. It's yes, please do the homework, get your credit, but it is not as important towards progress in class as presentations and running the code. It is a contribution to your education and understanding of the class material into two next classes. So do as time allows. If you can do it by coming Friday, credits will double. If your schedule is tough, it's okay to do it by coming Wednesday. And it is just basically practicing calculus, and for additional credit, complement the derivation that I will fail to complete during today's class. I just counted timing, and the material is not as important to postpone it to other lecture, but whatever, 40 minutes of class is not sufficient to do that. So one needs to find the value of constant n2, which makes normalization of this function equal to 1. And I will explain the context why it is important for the things we are doing. Okay, so I do have a dream 3 years to copy paste the best calligraphic version of this three-dimensional table in each lecture, but it is handwritten for each meeting over again. So we are browsing in the space of ideas, methods, and we already accumulated evolution operator, Schrödinger, time-dependent Heisenberg, equation of motion, concept of density of states. It was also density matrix somewhere. And now we are getting the concept of ladder operators, which are applied to the so-called harmonic oscillator, which represents interatomic motions in atoms or in molecules. And also this concept of ball in the spring, plasmonic nanoparticles. Actually, plasma also has oscillations in frequency. What else? LC circuit in radio. And one can do vibrations in solvent. So it is all harmonic oscillated. And since I am practicing laziness to solve time-independent Schrödinger equation for harmonic oscillator, instead we are doing ladder operators which give the same answer. And it is a little bit quicker. It's a little shorter. Okay. So, two lectures ago, we agreed to practice the Strawman once again. I'm not the best drawer, so it's a man going up on the ladder. So one can go up and down. If one goes one rung up, one rung down, as a result, one stays at the same level. which justifies the product of this two ladder operator up and down is giving energy. If one is trying to go lower than the lowest possible level, this operation gives zero. And when we implement practical implementation of this operator, we are finding the equation for the ground state of the harmonic oscillator, which looks like a Gaussian fully function centered at the equilibrium. And we also found the normalization, which is the square root of square root power 1 force, in order to have it normalized. By accepting the concept of these ladder operators, we are trying to get first and second excited states by applying creation operator. What else? Did I forget something in this story? The practical form for expressing creation and annihilation operators in terms of differential operators originates from the idea that going up, going down should give us energy operator. So we find such combination of position and momentum, because by now we don't know any other operators, which after being squared, it gives energy operator. So in some sense, this is my goal that I would like to achieve by the end of this meeting, but I just checked timing, it is not possible. So maybe it will be achieved by the middle of Friday. And there is a motivation for being very careful and specific about normalizing each state after we apply creation and annihilation operator. So I do not place a doubt in your skills in calculus. We all can practice application of this creation and annihilation operators as many times as we need, and there is no challenge, it's only time. So by applying derivative and multiplying by stuff, one would get the state, one would get the camels with 2, 3, 4 humps, right? And by practicing integration, one can do normalization. So why normalization is needed, and do I have any hidden desires towards this eigenstates and towards practicing of the creation and annihilation operators? Why should we waste your and mine, maybe less precious than yours, but our time in doing these exercises? Or why should we may neglect this ladder operators? Why should we do strict mathematical problem of eigenvalue problem and making sure that they are all normalized? I think I'm speaking rather than showing, so I can approach you closer. The trivial answer, the normalization is needed for being able to find expectation values, to make a bridge between abstract calculations and practical observations. But there is one more thing. We do want to confirm our original idea from where we started, that multiplying creation and annihilation operator to any state will reproduce the state, and with appropriate factors, it will be energy operator. We already used it as an input in the format of operators as in differential form. right? But when we are doing strawman jumping between steps of ladder, in some sense, one can practice this browsing through eigenstates without any differential operators. And it would be really cool if we set up this creation and annihilation operators in discrete form, not in differential form. So to avoid any calculus and differentiation. Last thing before we started harmonic oscillator was Schrodinger equation in discrete form, right? When in matrix form. You may eventually remember. So instead of continuous wave functions, we had just discrete states. In many practical situations, it is quite beneficial and comfortable move. We may want to practice the same stuff for the harmonic oscillator. So to go into discrete space and apply transitions between them, just as a matrix with element. Here is the probability of transition. Here is the matrix element, how this transition is happening. And when we are going to build this story, when we are going to build the mechanics of these discrete operators, one needs to arrive to a situation when going up and down one step, independent on how high we are, we will reproduce energy. And in this aspect, one needs to check the following thing: whether the application of ladder operator to eigenstate of harmonic oscillator only promotes the shape of the wave function to the one we need, or it also adds a factor in front of it. And we can check it only with making sure the normalization is right. The result, and it's not a secret, you can look slides forward, you can watch recordings from previous years, so it's not a big intrigue. The result is that when we apply creation and annihilation operator, we not only promote wave function from one eigenstate to another one, we also accumulate multiplication of the wave function on a specific factor. And this factor will be the bigger, the higher the state. And this feature later on serves great help in simplifying everything like 100 times. So instead of differential operators, it will be just like a childish game, basically like straw man, nothing else. And one can be as powerful as one should be with differential operators without them. So the expected result along these lines is that by applying creation operator to the lower rank eigenstate, one is getting higher rank eigenstate multiplied by square root of the number of the state. So multiplying creation to zeros, square root of 1. Multiplying creation to 1, then get 2, square root of 2. Multiplying creation to the 2, and get 3, square root of 3. Multiplying by number n, one gets n plus 1, square root n plus 1. So I really want to bring us to this idea. I have to suffer through some derivations, but later on it provides incredible speed up in practical things. When I was taking the same class in mind every times, either I just goofed up the lecture when it was introduced, or the instructor just decided not to introduce it, and I was having a headache for several years. I was lazy to read the book, but I was always asking myself, where are these factors coming from? And when it was time to instruct the course myself, there is a way to show it. Whew. Okay, and if you are fine with this idea, you will not hear anything else new during the meeting. It will be some boring derivations, and I I'm watching the time and I know that I will not be able to finish that. So it will be a waste of your and my time. If you have nothing else to do, you can listen on the background, but it will be nothing but additional ideas in order to prove this concept. So, in more details, we are going to apply, at the end of the last meeting, we got the first excited state, phi sub 1. Today we will take it, apply creation operator, and obtain the, just by three differential operators, that it will be x squared minus 1 times this exponential factor. And by doing normalization, after normalizing this function, we will arrive to the idea, we will arrive to the result that in order for this wave function to be normalized, one needs to divide it by 1 over square root of 2. So eigenstate number 2 is creation operator affected state number 1 divided by square root of 2. And then one can convert it in a little bit different form. Application of creation to number 1 gives state number 2 multiplied by square root of 2. So with expanding to higher orders, just extrapolating, applying creation operator to number n, we will give n plus 1 square root n plus 1. I think after this step, it's literally nothing new. I told all new information. So I cannot brag for this red box that it is my achievement. I took it from books. So if one defines the fraction between frequency and mass over Planck as like parameter alpha, then everything we do, this fraction, mass, frequency, Planck constant, comes again and again. So we just replace 4 symbols onto 1, saving our mechanical effort in writing or in typing. So M omega over d bar will be defined as alpha. And then the first excited state will be linear times Gaussian with the normalization factor. And our goal is to apply the creation operator, which is a superposition between position and momentum. We agreed to pull 1 over all constants out of the brackets, and then momentum comes without factors, and position has mass and frequency. I do have planned to do a mini quiz sometimes in the middle of next lectures, just to practice memorization of this stuff, because I cannot memorize it. Maybe you will be able. Okay. Let me check, maybe I have less ugly typing. Less ugly typing. Yes, it's a little better. And let me, I'm always forgetting, let me just quickly go to the online and check. Oh, August. Hello, thanks for joining. So if there are any questions, please let me know. And August, if you missed the beginning, please consider to follow the link and make your choice in this table. So we will have presentations on Monday, And tonight I will cover all things which were not covered last night. So number 1, 3, 4, and 6 are taken. Spencer is debating between number 6 and number 8, and then there are few subjects available. And I will play open cards. I will try to convince Zane to vote for number 2. Yeah, because it is the hardest one, and you were personally visiting it. But we can communicate by email. Okay, yeah, thank you. Super. I really appreciate it. Okay, there were no questions, so I'll continue this stuff. So it's too many symbols. I cannot believe all of them are really needed. So here is our file 1. Here is our creation operator. And we are replacing momentum by its definition. So after replacing it by the definition minus I gives minus, and then we have Planck, frequency, position, and derivative. And if I would pull, if I will multiply left and right by Planck constant, h squared divided by h, then I believe we can remove the details of the constants and use our abbreviation of alpha. So please, if you find error in this derivation, please let me know. Any error you find in the class materials are worth credit. And from now on, in the next slides, I hope we will we will use only the alpha constant instead of the fraction of all other constants. So we just need to practice the derivative. Okay. What we do this time? Well, I can exercise it, but I'm not sure if this is really needed. X squared. So there will be at least 3 terms. 1 from the product and 2 from derivative. So alpha x squared minus alpha x squared by 2, just multiplication. And then we are applying the derivative of the product, right? So it will be minus dx minus x ddx e minus alpha x squared by 2. So here, this is 1. We have alpha x squared e minus alpha x squared over 2 minus 1. And here we are, by applying derivative to the exponential, we get the factor popping up to the front. Then we need to take derivative of the x square function, and then the exponential stays unchanged. Right? So what is the derivative of x squared?
2x.
Yes, 2x. And then we can cancel 2 here and there. And we see that minus times minus will be plus. So we have x in here times x in there, and we have alpha, and we have plus sign. So it looks very, very similar to what we have in the first term. Okay? So x times x squared, alpha, and then exponential. So alpha x squared e blah 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 on this one. So we can remove the whole stuff here and just put factor 2 right there. And here is the same thing in better calligraphy. So we have factor x squared minus 1 in this exponential function. How does it look like? You probably camel with how many humps? No. When we were in the first state, phi 1, it was looking this way, plus and minus, or opposite, minus here plus there, right? So it was linear times exponential. Here we have exponential times second order polynomial. Let's double check it. By following the progression of same as particle in the box, and we got it abstractly and philosophically. The higher the energy, the larger number of humps. 1, 2, 3, right? But we need to prove that this idea is correct just by maybe some simple arguments. Let me draw. I would just like to draw, but you can see it. So we have 2x squared minus 1, which is x squared function. And then if we do minus 1, it means we either we just shift our axis higher up, right? Or shift the function down. Now we have exponential, not the Gaussian. And now we need to evaluate the signs. So Gaussian will be plus everywhere, and the x squared will be plus, minus, plus, and we'll have 0 at 2 points. Right? And now we need to draw a function that will cross zeros into points. And now we need to evaluate signs. So before first 0, plus times plus will be plus. Minus and plus. And then another feature is that at minus infinity it is 0, at plus infinity it is 0. So we need to build function that satisfies this condition. So we start from plus 0, going up, then going to 0, going down, crossing. Right? And if you take absolute value squared, then it will come to 3 humps. And if it is wave function, it oscillates positive and negative. Okay. 9 minutes more. So things do not change with years. Yeah, here is this creature with 3 humps. And this is a figure that one often observes in textbooks. Do you ever saw it? Not yet. I promise you, no matter what you are reading, this figure is it's kind of crazy and not logical, but probably it combines several concepts in visually appealing for some people way. So on the x, it is elongation, and on the y, it is a summation of wave function squared, absolute value squared, plus energy of the state. And the green line here is potential. So we draw the probability distribution, absolute value squared of the functions, but we offset them up depending on whether how big is their energy. Right now, we didn't solve for the energies of the eigenstates. Although it will be quite simple and quick, I want to declare just right now. So the energy of the lowest state will be positive and bigger, positive and bigger than zero. And it will be in units of Planck constant frequency at 1/2. This correlates with particle intervals. The energy due to confinement was bigger than zero, right? The stronger the confinement, the bigger the energy of the lowest state. Here, the frequency is related to the curvature. So if the curvature of the parabola will be more steep, if the whiskers will go up with higher curvature, this energy will increase. And also frequency includes mass. If mass is small, whiskers go up and energy goes up. If mass is heavy, then the parabola will be more shallow and this ground state energy will be lower. And then when you get first excited, second excited, they differ by h bar frequency, right? So 1/2 plus 1 will be 3/2. 3/2 plus 1 will be 5/2. I just postpone proving or showing it, it's just declaration. And then, in some sense, this image summarizes the whole chapter on solving time-independent Schrödinger equation for harmonic oscillator. Okay. And there is a thing that I have no way to complete in the remaining 5 minutes, and it will be extra credit for the whole. So if we want to transfer from continuous space of position differential operators to discrete operators, we need to find relation between acting by creation to the operator and getting another one and normalized wave function. We need to get a factor between them. We need to do normalization. So this one looks like, let me check if I have better writing. If no, then I need to use this one. So the second excited state is 2 alpha x squared minus 1 polynomial Gaussian function and unknown coefficient. We can pull the coefficient that we had in zeros and first state and then start from there. But if we do normalization, it doesn't matter. We can put it as unknown and do it from scratch. So we need to do absolute value square of this function and make sure that it is equal 1. So we need to solve it for n sub 2. If I am taking absolute value square of this function, I do see that this is subtraction of 2 things, like a minus b squared. So it will be 3 terms, a squared minus 2ab plus b squared. So b squared is the simplest, it will be 1. A squared will give 4th power, minus 2a times b will get the 2nd power. And then each of these terms is multiplied by minus alpha x squared. So over 2 disappears because of this code. And we need to take this integral. So this is a little too bulky to do at once. So we can follow the principle of ancient Romans, divide and conquer. So we'll divide it, we'll assume that it is not one integral, but 3 integrals, depending on the power of the polynomial. So 1 is x to the power 0. So it will be I naught. So 1 times exponential, integrate over the whole space. And we know from immediately that integration of Gaussian function will give like square root of pi, right? So this is the simplest thing that I probably can do in the remaining time. If we go to the higher powers, then it is like x squared times Gaussian, or x force times Gaussian. This is doable. It's not like by integrating by parts. It's like additional 10-20 minutes, but we do not have them now. And to make more comfortable integration, one can make a change of variables. So square root of alpha x as a new variable. Then it will be just literally e to the pi minus xi squared. Okay. So 4 integrals. First, second, and third. And then after practicing each of these integrals, we need to add them together and make sure that n sub 2 squared to the square root of alpha times sum of these integrals is equal to 1. And after solving for it, one would observe that the normalization factor differs from blank application of the creation operator, the first excited state, by the factor 1 over square root of 2. It's kind of answer that one needs to obtain if you go for isoperiodic problem 6 for the homework. Okay, done. Everyone is welcome to disappear, disconnect, and I'll check if there are questions online, but we are done. And I believe we're done in time. So looking forward to see you tonight in the lab. If your schedule doesn't allow, I hope the recordings will go fine, and I'll share it by about midnight. Okay, I'm going to disconnect unless anyone stops me. 1, 2, 3.